Okay, cool. So hi everyone. Today I will talk about multilingual NLP. Before I start out, are there any questions or things that people have? No? Okay. Let's go ahead. So this time I'll be talking about multilingual NLP, which is obviously NLP in lots of different languages in the world. And however, we can kind of split it into two different varieties of multilingual NLP. The first one is monolingual NLP in multiple languages, or namely, usually people refer to multilingual NLP and they actually mean NLP not in English. So this can be, any variety of tasks that we would do in English, like QA, sentiment analysis, chatbots, code generation, other stuff like this. Then we have cross-lingual NLP, and cross-lingual NLP is where we actually have multiple languages involved. This could be machine translation, it could be cross-lingual question answering, other stuff like this. So I would say by far the biggest barrier to multilingual NLP is the paucity of data. The fact that we don't have enough data in all the languages that we would like to be handling. There's a big disparity in the monolingual data that's available for training. This is just an example from Wikipedia, and this is the number of Wikipedia articles in different languages. And you can see there's like a very, very long-tailed distribution of the Wikipedia articles in different languages. It's a little bit, I think Wikipedia is a little bit less, it's a worse situation than the internet overall. Like the internet overall, I feel is maybe a little bit less graded than this, but or a little bit less long-tailed than this, but the internet itself also has much more English than in other languages. And then there's even less annotated data for machine translation, sequence labeling, dialogue, chatbots, supervised fine-tuning, RLHF, you name it. So that makes it more difficult. I would say data is like 95% of the problem, honestly. And then the other 5% of the problem is linguistic peculiarities. And so some languages are different than English in a number of ways, like you learned in the linguistics class. And most methods are tested first on English, but not all languages are the same as English. So maybe the biggest difference that we have to deal with is rich morphology. So we talked about morphology in the linguistics class, but does anyone remember a type of morphology that would be like particularly bad or particularly difficult to model using the assumptions that we make in English? Anybody remember the linguistics in the linguistics class? A language that we talked about that had particularly difficult morphology? So yeah, something like Hebrew or Arabic, there's a lot of examples where kind of you have the consonants form the root of the word, and then you put the vowels in the word depending on the conjugation. And this is bad for things like BPE, for instance, because unlike English, where the root is a contiguous set of characters, in these words, it's not a contiguous set of characters. So this is called infix morphology, and that can cause issues. Another thing is accents and diacritics. So we can have, tonal accents and stuff that are written on particular words, and this can cause issues. Different scripts, like CJK scripts, Chinese, Japanese, and Korean. Each character has a lot more information than we have in English character. And so, the segmentation methods might not work as well. We can also have dialects where, people speak differently. It's, kind of one language, but people speak differently depending on, their social background or something like this. And another really big issue is lack of formal writing systems. So, English and a lot of other, particularly European, but, also some Asian languages have a very strong formal writing system that was imposed from many, many years ago. So everybody who's literate in the language writes spelling more or less the same way. But there's a lot of languages where this is not the case, like many languages in Africa, many languages in India, other things like this, where there's not really a really strongly agreed upon way of spelling. So this increases the variance in the languages and makes things more difficult. Cool. As an aside, if we talk about dialects, there's a pretty big interest in dialect processing. The idealized definition of the difference between a language and a dialect is that dialects are mutually intelligible. So if you speak a dialect, if you speak a dialect of English, I will still be able to understand you. But in reality, there's a saying, a language is a dialect with an army. And what that means is you might call something a language just because two different countries speak it, but actually it's almost completely mutually intelligible. So does anyone know any languages where this is the case? Yeah.
Serbo-Croatian.
Yeah, exactly. So a lot of the languages from Eastern Europe are like this because the languages from Eastern Europe are not actually that different, but they are from different ethnic groups that maybe don't like each other very much. So neither one of them wants to acknowledge they speak the other ethnic group's language. And another example of this, in India, they speak languages. In China, they speak dialects. It's just because that's what the government decided. In India, that the government decided they would call them languages. In China, they would call them dialects. But in reality, some of them are mutually intelligible, some of them are not mutually intelligible, other things like this. So processing dialects is similar to processing languages, just because a language and a dialect are not all that different, or a dialect is not all that different from a very similar language. But there are lots of problems that are kind of like political/logistics problems that make things difficult. For instance, some languages are not, or some things that are called dialects are not even registered in the list of languages that you can get from the ISO. So like actually the ISO has an official list of language codes. They used to be 2-letter language codes like EN and ES for Spanish or other things like this. Now we use 3-letter language codes. So like the standard is called the ISO 639 standard, but many dialects don't get their own language code. And so they aren't listed here purely because they're called a dialect and not a language. A lot of major things that are called dialects still get their own code, but if you get more minor, that's kind of a significant difference. Cool. Any questions about this? And actually, in reality, like when people tell you like you have an accent or you speak a dialect or something, like everybody has an accent, everybody speaks a dialect, right? I have an English accent and I have an English dialect, even though my English accent and dialect are kind of pretty close to the standard American English that's taught in schools. But I have a slight accent, so people can place me, people from America who know dialects really well can place me from where I came from, for instance. Okay, so now let's move on to multilingual learning. We'd like to learn models that process multiple languages well. And the reason why is this allows us to do transfer learning, so we can improve the accuracy on lower resource languages by transferring knowledge from higher resource languages or abilities from higher resource languages. Another thing is there was a time not so long ago when people trained a different model for every language that they wanted to handle. And when they did this, they had to deploy a different model for every language that they were processing. And this was, a major issue if you had lots of servers and you had one server serving your, Japanese model and one server serving your Spanish model and one server serving your Chinese model and stuff. So now if we can have a single model that does all of these, it works. It can deal with things that are cross-lingual and other stuff like this. So this is now like basically the standard that everybody uses. So this is kind of a high-level multilingual learning flowchart about how we go about multilingual learning. And if we start at the top and ask if we have sufficient labeled data in the target language, that's a great thing, of course. The next thing we need to decide is, do we need to serve many languages with strict memory constraints? And in this case, we would generally make a multilingual model. If we don't need to serve many languages, or we have, all the memory or machines in the world that we want to use, we can also try to adapt specifically to a single language. And, if you're at a big company in France or Japan or something like that, you might really, really care about French or Japanese, and then this is still a very, reasonable choice. If you don't have sufficient labeled data in the target language, you have a couple options. If you have annotators who are speakers, you can do annotation or maybe even active learning, which we'll talk about. And if we don't, then we have to do zero-shot or adaptation or kind of weakly supervised adaptation or other stuff like this. So I'll start out with multilingual language models. So if we think about simple multilingual modeling, it's possible to learn a single model that handles several languages. You can just process different inputs with the same network. So if you have any of the major models nowadays, they're usually trained on multilingual data to a lesser or greater extent. And if your job is always to translate into English, you can just tell the language model, translate into English, and it will translate into English regardless of what the input is. You don't even need to say, this is a French sentence, translate into English. This is a Japanese sentence, translate into English. If you have multilingual outputs, then at the very least, you need to add a tag or a prompt about what the target language should be. Starting with Google's neural machine translation system in 2016, it has been frequent to add a language tag that says, okay, French, this is an example, Japanese, this is an example. And then you train the model where you append this tag and then generate the output. Very easy to do if you're training a model. If you're not training a model, but you have a language model that accepts instructions, then you could just say, please translate this into French, please translate this into Japanese. So that's a common way to do things. There's a few difficulties here in fully multilingual learning. There's a famous paper from 2019 that points out something they call the curse of multilinguality. And the basic idea is, for a fixed size model, the per language capacity decreases as you increase the number of languages. So this was the way we read this graph is, this is the number of languages that they included in the model training. This is how well they did on the low resource languages in blue. This is how well they did in the high resource languages in orange. And then the gray is the average of the two. So you can see that as you scale up the number of languages, they do a bit better with the low resource languages, but the quality of the scores on the high resource languages goes down gradually and then kind of abruptly as you start scaling up the number. And basically, as you increase the number of languages, it decreases in the quality of high resource language translations, other things like this. And this is just hard in general. This is a hard problem to solve, because if you have a limited amount of either model capacity or compute, you kind of need to decide where you're going to allocate it. And actually, there's another kind of more recent paper that I should that I can also share.
This depends on the languages that you're like maybe there are some languages that kind of overlap more than others.
Yeah, that's a great point. Yeah, sorry, I wasn't able to quickly find the paper there, but this does depend on the languages you're using. So if you're using very similar languages, this can benefit a lot. This one, you see they're scaling up to 100 languages, and these are not picked specifically for language similarity. So yeah, that does affect. But if the languages are similar, you can see some benefits. And I'm going to talk about that actually a little bit more in a second. Another issue is tokenization disparity. I actually already talked about this right at the very beginning of the class, but just a refresher. If you look at English, you can see that the GPT tokenizer gives this prompt basically 58 tokens because the tokenizer was trained on lots and lots of English. But if you do it in Burmese, then this is the same content. It was, translated using Google Translate, and we get 617 tokens. So it's more than 10 times the number of tokens because the tokenizer was not trained on Burmese. And so, yeah, this causes problems both with respect to modeling and with respect to cost. So a very common way to fix this is through heuristic sampling of data to try to better balance the language distribution of the data. And this is a method called temperature sampling. And the way it works is if you have higher resource languages that have lots of data, so this is kind of illustrative of that, and then you have lower resource languages where there's very little data. Let's say you have 1,000,000,000,000 tokens in English, and you have 1,000,000 tokens in Burmese, for example. That would mean that you would essentially sample English 1,000,000 times more often than you would Burmese. So what we do is we basically where's my chalk? So the last class, most of you used all the chalk. If you saw the whiteboard, it wouldn't be surprising. So basically what we do is we do the count of language L, and we exponentiate it to 1 divided by tau, and then we have the sum. And so if we set the temperature to 1, basically that means we'll sample all of the languages proportional to the amount of training data they have. If we set this to infinity, that means that this exponent becomes 0. So the count becomes 1, or this value becomes 1, regardless of what the count is. So that means you would sample each language with equal probability. And if you sample each language with equal probability, that's kind of like fair to all of the languages, but it also means you'll totally overfit the languages with very little data. So you can do something in the middle where you set this tau to like 5. And that means that you sample the highest resource languages a lot less, the lower resource languages a lot more, but still you have some balance where the higher resource languages get more samples. So this is very common. This is used both in the construction of the vocabulary and in the sampling of the training data for pre-trained models, for instance. All clear? Okay. There's also other methods. So this is a method that one of my students, Cindy Wong, examined. And basically what we did is we had a development set. We had a development set of data. And this development set is all the languages that we want to be able to model well. And so this could either be like an equal amount of data from every language, or it could be like only data in, Indian a particular language family from India or something like this. Maybe we want to create a model that's specialized. Then we have our training data, and this is all the data that's available to us, maybe separated by language. And so what we do is we take the model, we calculate some gradients. calculate some gradients from the data, and we find the level of alignment of the gradients between the development data and the training data. And if the gradients are more aligned, basically the score will increase. And if the gradients are not well aligned, the score will decrease. And then that gives us a new probability distribution for the various sets of data. And if the gradients are aligned, what that means is that training data is helping you move in the right direction to improve the loss on the development set. And if they're not well aligned, it means you're not. And if they're misaligned, if they're pointing in opposite directions, it means that training on that data will actually hurt the development set accuracy. So this is a way to kind of do balancing of any variety of data, but in particular in this paper, we looked at multilingual learning. And I think this is exciting because it allows you to, upweight data as necessary. But if you start overfitting, then it will get downweighted through the training process. So you can also learn a dynamic curriculum. Cool. Any questions there? Okay, next. Let's move on to machine translation. So machine translation is one of the biggest, multilingual tasks, very, very important, very valuable to a lot of people. And so, this is an example. You have English, and then you would translate it into some other language like Spanish. But it's actually really difficult to translate well, even for human translators, and of course for machines too. And a couple of reasons are syntactic divergences between languages. So if I write the development of artificial intelligence is a really big deal, this is what it would look like in Spanish. And if you speak Spanish or any Romance language, you'll notice some typical differences between them, like artificial and intelligence swaps in order. Yeah. And another one is, this is into Japanese, and it's even crazier because the two languages have very different syntax. Another thing that makes it a little bit tricky is things like big deal. Big deal are like colloquial expressions, so you can't just translate word for word. And so because of that, you also need to be aware of things. Another thing is contextual differences in translations. So this is an example of a translation of the word leg. And depending on what type of leg we're talking about, it will be translated differently. And so if it's a journey, it would be translated this way. If it's an animal leg, it would be translated this way. A chair leg, it'd be translated this way. A human leg, it'd be translated this way. And if you speak any other languages, I'm sure you can come up with examples like this. The worst words overall are something we call light verbs. These are verbs like do, have, and things like this. And if you can think about all the things that you can do or all the things that you can have, there's probably like 50 ways that you could translate those into different languages. So there's a number of translation tasks that people evaluate on. The first is the Conference on Machine Translation, abbreviated WMT, which is a little bit weird, of course, if you see that conference doesn't start with W, but there are historical reasons for that. There's also the Flores dataset. So this is a popular dataset that was created by Meta. It's in 200 languages. It's translated from English Wikipedia into the other languages. And I kind of like the overall idea of this data set because it's basically like we would like universal information access. And if we could translate English and Wikipedia effectively into all the other languages in the world, that would be, pretty beneficial. Of course, there is information that's on other Wikipedias that isn't in English Wikipedia, but as you saw, English Wikipedia is the largest and it has the best coverage of like scientific topics and other stuff like that. So I think this is pretty attractive. There's also IWSLT. So this is a speech translation conference and it has tests on speech translation. For automatically evaluating MT, we talked about this in the place where I was talking about human feedback a bit, so I'll just go through it briefly. But we have BLUE, which is based on overlap of token n-grams. So if you have the big dogs and big dog, you would have a single token, and you would count that, let's say, big dog and home and home. And so you would get 3 unigrams correct and 2 bigrams correct. And then you count all the way up to 4 grams, and that's you combine them together using the geometric mean or harmonic mean. And the problem with this, though, is this doesn't consider paraphrases or morphology or anything like this. So, for instance, dog and dogs would not be treated as overlapping just because there's an S on one and no S on the other. So, actually, cat or hippopotamus or something like that would get the same score as dog in this case, and that's kind of a problem, right? So, BLUE does have the advantage of being extremely simple because you don't need any language-specific processing other than tokenization to make it work. But you do actually need tokenization, so you need to be able to split kind of like commas off of words and other stuff like this. KRF, I strongly prefer KRF over BLUE. So if you're doing machine translation research, I'd just say you can almost throw away BLUE and just focus on KRF. And the way KRF works is it's based on character engrams instead. And so a character engram would count like all of the pieces of dog, even if the S was wrong. So this gives you kind of more robustness, better correlation with human judgment. Another popular embedding-based metric is called Comet, and there's a bunch of different versions of Comet. It's used very widely in translation tasks. And then there's also a number, like many different language model-based metrics where you basically ask an LM to assess how good the outputs are. And I would say the LM-based metrics are probably the best ones at the moment. But the problem is, like, if an LM is bad at translating it, it's also not all that great at assessing it. So if you were evaluating translations into low resource languages, I'd recommend at least using KRF and like one of these kind of embedding-based or LM-based metrics. So for translation models, there's 2 main ways of doing translation nowadays. One is just ask a language model. And the other is to train a specific translation model. The best translation models that are public right now nowadays are created by Meta's translation team. And they have one called NLLB that's pretty well known. And the way NLLB works is they start out with some seed data in public bytext data, monolingual data. And then they train a model to do bytext mining from existing data sets, mine this bytext, and then take the mined bytext and the seed data that was kind of pre-curated and use that to train a multilingual translation model in 200 languages. And they evaluate it on Flores, make sure that it's not toxic, and then they evaluate it with human evaluation. They also have to do language ID and cleaning. They have a lot of modeling techniques that they include in here, mixture of experts models, curriculum learning where they start with kind of low quality data, including low quality data, and fine tune on high quality data. Another thing is, in order to incorporate monolingual data into translation, the most common way to do that is through back translation. So basically, like, if you have English data, if you have lots of like monolingual English data, you first train a model that translates it into, you first train a seed model, and then you translate this data into your source language. So if it was Japanese, you would translate it back into Japanese. And so you'd have like English, and then you would have Japanese prime, where Japanese prime is like automatically generated Japanese. And what you typically do is you only use this data when you're training from Japanese into English. And the reason why is then you would get natural English, but possibly unnatural Japanese. And so that ensures the fluency of the generated output, basically. So that's back translation. So how do we do bytext mining? How do we do mining of high quality parallel data? The way we do this is through bilingual embeddings, or the way that NLP does this anyway is through bilingual embeddings. And the way they do this is they start out with just, a model, a standard embedding-based model like BERT or any other masked language model. And they have bytext data and monolingual data, and they train using a loss where they try to optimize the cosine similarity between positive examples and minimize the cosine similarity between negative examples. And we talked about this in the retrieval class, right? So it's kind of a contrastive loss where we have in-batch negatives, and we can get in-batch hard negatives and other things like this. So this is a basic way of doing this. One really interesting thing, if you're doing any sort of kind of semantically similar sentence mining task, is they have an objective that has proven really useful for this sort of bytext mining. And the way they do this is they get the cosine similarity between the two instances. And then they also have the cosine similarity between each of the instances. And they have the margin between this and the similarity between all of the other nearest neighbors. And the reason why they do this is there's a problem, especially in high dimensional spaces, called the hubness problem, which is that there's a lot of instances that are just very similar to like 500 other instances, because maybe maybe you have a space that looks like this, and the one in the middle is close to like a bunch of other ones. And so what you want to do is you want to make sure that these hubs don't get selected all the time. And this kind of normalization over the nearest neighbors allows you to avoid this sort of hubness problem. So if you're interested in any sort of mining task using embeddings, then this is a good thing to know about this XSIM function here. Cool. Any questions? No? Okay. So another question is, wait, but do we need to train a language model at all? Or sorry, do we need to train a translation model at all? Couldn't we just use a language model and ask the language model to translate for us? And the answer is language models out of the box are reasonably good at translation for high resource languages, but for lower resource languages, they're quite a bit worse than kind of custom created translation models. And you can see from this is a comparison between the NLP model that I just talked about. It's the open source translation model and GPT, and measured according to KRF. So in the highest resource languages where we used number of Wikipedia pages as a proxy for high resourcedness, and this is our paper, which is why I'm saying we, but you can see that you get the highest scores from GPT on these high resource languages. If you move down a quartile, you get lower scores and lower scores and lower scores. And And, a custom-built model like NLP can do better. One small caveat that I should point out here is that CareF is a lexical metric. So it's still based on kind of like word overlap and stuff, and it's not particularly good at picking out paraphrases and other things. So I think this is actually somewhat underestimating the quality of the GPT models. So I think the GPT models will tend to do better at these other metrics. And these other metrics are also correlated better with human judgments. But the problem is if we go down to like the 100th most popular language in Wikipedia or 200th most popular language in Wikipedia, we don't have any good embedding models, or we don't have any good language models for them anyway. So we trusted CareF more as a metric in this case. Cool. But there is some hope for using language models for these tasks. So we have multilingual pre-trained models, and standard LLMs, closed LLMs such as GPT-4 are typically incidentally multilingual due to large training data. And unfortunately, a lot of open LLMs actually do data filtering to allow for good performance on English. So they'll actually filter out multilingual data and train mostly on English just because, they have a limited amount of compute and they want to get good scores on English. So they remove the multilingual data. So that's unfortunate. But there are some kind of like open multilingual models. I just realized I'd like to point out one more thing that I forgot to point out. So there's this paper from a little while ago from ACL last year. And basically, what they did was they looked for data where it was incidentally bilingual. And what that means is it's like a book online about learning how to speak a language, or it's, translated caution directions on, from a product or something like that. And those happen to be bilingual. They happen to have a document with the same bilingual text in it. And there's actually a relatively large amount of this data on the internet. And so the zero shot, they used it to mine prompts to improve zero shot translation quality. And they measured that 1.4% of all training instances were detected as bilingual, and 0.34% contained at least one translated pair. So if you're wondering why, language models already are able to do things like translation, that kind of gives you the answer, right? Like 0.34% of their data actually is translation training data. And so because of that, they are able to learn to some extent, even if not explicitly trained that way. But there are a lot of efforts to explicitly train them to be better at multilingual tasks like translation. And so the first thing I'd like to talk about is representation learning. So how do we learn multilingual representations? And things like BERT use mass language model objective. And there are models such as MBERT and XLM, XLMR, which extend BERT for multilingual pre-training. And there's two most common ways to do this. The most common way to do this is multilingual masked language modeling. And this is also called translation language modeling. But what they do is they create a masked language model where they mask out some of the values on the source side, some of the values on the target side, and then they try to predict. And the basic idea is, in order to do this task well, you kind of need to form correspondences between things in one language and another language. And so this allows you to learn in a kind of very lightweight way how to do multilinguality. There's also some more explicit alignment objectives. And this is one example. So in this example, they do something called cross-lingual word recovery, where they calculate the representations in in one language, and then they have a softmax that tries to pick out the most appropriate representation to use. And then based on that representation, tries to predict something in another language. So this is a little bit more explicit. There's also objectives that try to match alignments between the different sentences. And so they train, they get alignments from an a priori alignment model, and they try to make sure that the attention, sorry, no, this is not from an a priori alignment model. This is the attention objective, and they try to match the trace between the attention from one language to another, and like language Y to language Z, and then language Z to language Y. So language Y to language X, and language X to language Y. So what this does is this tries to make the attention look similar between the different languages, regardless of the direction you're going in, and so that can improve alignment as well. So let's say we trained a multilingual representation learning model or a multilingual language model. How do we evaluate it? The most typical way to do this is through either evaluating on a specific multilingual data set or evaluating on composite benchmarks in many different languages. So for the kind of older representation learning evaluation, the most common data set for this is a data set called Extreme, which was created by Google and one of the students in my lab, Junjae Hu. And this includes things like sentence classification, structured prediction, sentence retrieval, question answering. And then there's also other versions of this. Extreme R is harder version of Extreme, and Extreme S is a speech version of it. And then more recently, there was this mega benchmark, and the mega benchmark is kind of more directly suited for multilingual LLM evaluation, and they evaluate multilingual LLMs on many different kind of related tasks. So these are some methods you can use for representation learning and evaluation. There's also explicitly multilingual pre-training methods or continued pre-training methods. So one of the original methods for this was MT5. And MT5 is a multilingual version of T5, an encoder-decoder based pre-trained model. It was trained on many languages, achieved high performance. Even now, it's reasonably competitive just because it was trained explicitly to be multilingual, as opposed to many of the other ones that were trained kind of multilingually, but more incidentally. But fortunately, in the past months, basically, there's been also maybe past year, I guess. There's been a few nice developments in explicitly multilingual language models that are actually pretty competitive, even on English tasks. So one model is called Aya-23, and this is 8B and 35B autoregressive LMs. The pre-training was based on a standard pre-trained model with relatively good multilingual balance, so Cohere's Command R model. And then this was fine-tuned on a lot of multilingual data. So they had kind of templates that they used to create multilingual data. They also had a huge kind of community annotation effort where they created 204K examples of human-labeled data, translated data, synthetic data. So this is kind of one of the most explicitly multilingual models that there is available. Separately from that, there's a model called Tower, which was created by a company in Portugal called Unbabel and a few universities. And this is an 8B autoregressive LM. It was specifically created for translation and other translation-related tasks. So in contrast to Aya, which is more focused on multilingual, on monolingual tasks, but able to do them multilingually, Tower is explicitly trained for cross-lingual tasks. And they did pre-train, they used the Llama pre-trained model they did continued pre-training on translation and filtered monolingual data, and then did fine-tuning on multilingual instruction tuning data. And they actually found that they were able to achieve quite strong results on translation tasks. And I believe a model based on this actually won the WMT 2024 evaluation, which is kind of the gold standard evaluation task for translation models. So this demonstrates that LMs are pretty promising for translation tasks as well. It demonstrates that they're promising, but they're building on kind of the back of the NLP models with respect to data curation and other stuff like this. Yeah.
But like when we're pre-training these like large models, like I think it was mentioned earlier in the class in previous lectures that a lot of data online is already translated text.
Yep.
Which might be erroneous in the first place.
Yep.
So how does that affect like the pre-training?
Yeah, it's a great question. I don't know if there's any perfect solution to this, but there are some solutions, and I can actually go back to the NLP slide to demonstrate this kind of stuff they do. So they do language ID, for sure, and so they try to identify things that have a high probability of being the right language. They also do cleaning. So I don't remember exactly what the NLP cleaning involves, but very often it includes kind of like very simple filters, like length filters. So if a sentence is like more than 2x the number of tokens in one language, you just throw it out. And then you think they also have a kind of threshold for lasers. So if the laser score is way too low, then they throw it out too. So that will get you a lot of the way there, but it doesn't get you all of the way there, of course. So. Cool. Any other questions? Okay. I'd also like to talk about some other modeling strategies, or at the very least, training strategies. And so if you're training a model to be particularly good at one language, cross-lingual transfer learning, basically, you try to do multilingual learning, or you can do pre-training and fine-tuning on the target languages that you're interested in, zero-shot transfer. And then there's also a method called annotation projection, which can be used for supervised tasks. So pre-training and fine-tuning, is very simple. You just pre-train on many languages, and then you fine-tune on a language that you're interested in. But there's also another method where you can actually pre-train on all of the languages in the world and then fine-tune only on languages from the same language family. And this can improve performance. So if your target is Belarusian, you might also train on Russian, because Belarusian is pretty close to Russian. Another interesting modeling strategy is meta-learning for multilingual training. This is large-scale meta-learning is not super practical in language models. It is possible, but it's very hard. But I haven't talked a whole lot about meta-learning because of this. But just to give a very high-level idea of meta-learning, the idea of meta-learning is you want to learn parameters that are not good for solving the task, but parameters that are good, essentially initializations for future training. It is one common variety of meta-learning. And so what they did in this paper is they, instead of doing multilingual pre-training and then fine-tuning, they did multilingual meta-learning, where they tried to learn parameters where the first gradient steps in a new language would give you a large decrease in loss. So what that means is, instead of learning the parameters over here that are good for like French and Spanish and Portuguese, you would learn something that's a little bit closer to your target languages, because that would, give you a better increase in loss after you start training on them. And the way you do this is similar to how we did the data balancing. The data balancing work that I talked about was also based on meta-learning, but you do this by finding things with good gradient alignment with your first steps on this language over here. If anybody knows more about meta-learning, this is basically MAML. MAML is a common variety of meta-learning. Yeah, this is possible. So you can learn models that are good initializations for multilingual training. So another thing you can do is zero-shot transfer for pre-trained representations. So basically you pre-train the model, and you could, for example, pre-train a large language model using monolingual data for many languages, and then fine-tune it using annotated data in a given language, for example, English, and then test the fine-tuned model on a different language from the fine-tuned language, like French. In multilingual pre-training, allows you to learn kind of language universal representations so that this actually works. This is very surprising in a way, but it like actually does work. It especially works for simple classification tasks like topic classification. And the reason why is, kind of related to what I talked about with, actually, I won't go to the slide, but it's kind of related to what I talked about with the like incidental multilingual data. Like if you have 0.34% of your data is incidentally multilingual, you kind of for free get translation language modeling across that data when you just train on all of the internet. And then separately from that, there's a lot of linguistic similarities between English and French, for example. So it's easier to optimize the objective if you learn to put English and French words in a similar part of the space if they're semantically similar. So it's quite, it might not be super intuitive at first, but you can actually do a pretty good job of transferring even in a zero-shot way like this. Another method is called annotation projection. So this is a very old idea from 2001, but it's still applicable nowadays. And the idea is, let's say you want any variety of annotations for a language, particularly a low resource language. So like, let's say you want parts of speech, or you want entity tags, or you want something else like this. What you do is you tag, for example, English text, then you use a word aligner to align words between the English text and the French text. And based on these alignments, you can essentially project these tags or any of the other data that you want into the other language. And so if it's like, if you're doing parts of speech, you can do like, okay, this word is aligned to this one, this word is aligned to this one, and then just project parts of speech. But then you start running into problems if you have like one word aligned to 3 words or other stuff like this, it becomes less clear, but then you usually would come up with some sort of heuristics to solve that problem and get supervised training data. And this will give you supervised training data for any sort of tagging task or analysis task in the other language. It's also really simple to do. Like, let's say you want to train a topic classifier, you just do topic classification in English and then project it into the translated data. I forgot one very important thing, and the very important thing is like, how do you get word alignments? So let me just pull up a paper. There's a number of different ways to do this. This is my paper, but it's also one of the most widely used ones nowadays, I think. And basically the idea is you get embeddings between the for each token in one language in another language, and you can calculate similarity scores between the token similarities of the 2 languages, and you can like take the average in both directions or something like this. And if you take the average of the cosine similarity, or if you, yeah, there's a variety of things you can do, but actually this is a simpler example than the thing I mentioned with taking the average. So here, this is just a similarity between the embeddings. And so then you find the top 1 similarity out of all of these similarities, and you annotate it, and then you might find the next highest similarity and annotate it, the next highest similarity and annotate it. And then just go through until you have a 1-by-1 alignment, and then the ones that are remaining, you can do like one-to-many alignments and other stuff like this. So this is what happens when you do this naturally on the left. And you just do it with the existing token embeddings from something like Multilingual BERT or something. This one on the right is after supervised fine-tuning. So we did supervised fine-tuning to fine-tune the model to upweight alignments that are included in supervised alignment data and downweight alignments that are not included in supervised alignment data. So this is the paper, word alignment by fine-tuning embeddings on parallel corpora. So it also has a software toolkit called Awesome Align. I didn't name it Awesome Align. I'm far too modest to do that, but the first author thought it was very awesome, so he decided to do that, and I don't disagree. But yeah, so that you can do for annotation projection. You can do it for any other variety of tests like that. Cool. So then the next question is which language to use when transferring from another language. And long story short, the more similar the language, the better. So if you are able to get, annotated training data in one language and you want to transfer into another language, having similar data in similar languages is the best. But the problem is, how do you define similar is tricky. And then separately from that, what if you have a really similar language with like 50 training examples and a not so similar language with, 500,000 training examples? Which one do you choose? Probably the not very similar language with 500,000 training examples. And so this is another paper from people at CMU who I worked with. And what we did essentially was we trained a huge matrix of all of the scores that you get by transferring from one language into another language. And we essentially trained a ranking model to try to decide which language you would be the best for transferring from. And that gives us kind of an empirical answer about which languages are the best to transfer from. And we did this for machine translation, entity linking, part of speech tagging, and dependency parsing. And what we found is that very surprisingly, the best single indicator of whether a language is good to transfer from is whether it is close on the globe. So whether the location is similar. And this doesn't make a whole lot of sense, right? Because you could have languages that are, like very, very different, but very close on the globe. Like, for example, some of the languages in China versus Thai or something like that are not like all that similar in grammatical structure. But it's kind of a good proxy for syntactic similarity and whether they share a lot of words and all of these other things. So actually, we found that to be the best one. And amount of data is important. How much the vocabulary overlap is important. And then if you use a ranking algorithm to choose the best one, you end up getting the best one more often than if you use any of the individual features. We did this work in 2019, and when we did it in 2019, we were using neural models, but we were using models that are much, much smaller than the LLMs nowadays. So my answer right now might be, well, don't just train on one language, train on all of them, and maybe that's better than, training on any individual language. But actually, another important thing is you might want to create data, like I'm going to talk about in a bit. And if you want to create data, you might not be able to create data in all of your target languages, and you'd want to maybe focus on creating data in, particular languages that are close to the ones you want to be able to process. So that's another thing. So what if languages don't share the same script? This is another problem. So like, what if you have a language that's written in a script that isn't very similar to any of the languages where you have training data? A good way to overcome this is to convert all of the languages into the same script. I mean, there's kind of issues with this, but for the purpose of processing, especially if you're just doing language understanding tasks, you can convert all of them into the same script and kind of resolve this issue. You have a couple choices here. If you remember the linguistics class, we had IPA, the International Phonetic Alphabet. And IPA is a reasonable choice because it talks about how languages are pronounced. And if two different languages are pronounced very similarly, that will map things into the same space. There is a problem with IPA though, which is, and we uncovered it in this paper that we did, which is we actually mapped English and French into IPA, and it dropped the accuracy by a whole bunch. Does anyone know French by any chance? So can you guess why that might happen? If you map English and French into their pronunciation, that hurts transfer accuracy. And when I say map into their pronunciation, I mean from the written.
Spelling?
Yeah, spelling.
Oh, like for example, H does not pronounce the H.
Yes. So the spelling in English and French is way more similar than the pronunciation is. So basically, by mapping into the pronunciation, you mess up the correspondence between these languages. So it's not a silver bullet. But like if you want to do something like this, you can use Epitran that was mentioned in Lindia's class by David Mortensen here at LTI. There's also another kind of simpler method. I think it's called. Actually, I think it was called Romanize Anything, or the Universal Romanizer or something. Yeah, you Roman. And what this does is this gives up entirely on IPA, and what it does is it just maps all non-Roman scripts into non-Latin scripts into Latin scripts. And the way it does this is within Unicode, every Unicode character has, or every Unicode character in a phonemic script has a description in English. And so they basically parsed those descriptions in English and used that as the way to Romanize the characters. So it's very rough, not anywhere near as well, polished as something like Epitran, but it can do the job.
Work for character-based languages?
Like Japanese and Chinese. It doesn't work for Japanese and Chinese, so they're doing something special for Japanese and Chinese. But Japanese and Chinese are I think the only existent or currently used logographic languages. Which is interesting because there's like 7,000 languages on Earth, but I think there's only 2 that are logographic, and they're major languages, so everybody thinks about them, but then there's actually no long tail there at the moment. If somehow we manage to resurrect Sumerian or something like this, which is a very old language that used cuneiform characters, then we might have to think about it again, but I think we're set for now. So the next question is, how do we share parameters in these models? The simplest way is sharing all the parameters, and this is what we use most frequently. We can also share only the encoder or only the attention mechanism. This is less popular nowadays. We also had a paper on sharing some of the matrices in the transformer model. Even a crazy thing where we tried to generate parameters for each language using a parameter generator. But one common way to do this that I think is still pretty relevant if you want to train the strongest possible multilingual models is using language experts. And language experts are like special parameters that are fine-tuned to adapt the model. And a lot of the kind of original work on doing this in 2020 or 2022 used adapter models. So if you remember from the parameter efficient fine-tuning, we talked about adapters, we talked about LoRa and other things like this. I think right now, nowadays, it makes a lot more sense to use something like LoRa for this, just because LoRa is a lot more convenient. It has better, implementation in existing toolkits and stuff. But anyway, the basic idea is you train language-specific parameters and use them to modify an existing pre-trained model. Okay, so a final thing I'd like to talk about is creating new data. And so if you're like really serious about creating good models for other languages, this is something you're going to have to do. And, you know, especially if you're in a multilingual team in an industry or something like this. So one way you can do this is you can just hire people to do the same thing you did in English. But the problem with this is this can be very expensive, especially like as we're moving to more complex tasks, like annotating a single thing in English can cost $50 for a highly skilled, you know, highly skilled person. And usually those people are in countries where the like wages tend to be lower. And because of that, you know, you're paying people a very good wage, but you know, it doesn't compare to, for example, paying somebody in Finland a very good wage. So, you know, if we start talking about multilingual data for, you know, Japanese, Finnish, you know, other places where most of the people live in very high, you know, highly paying places, then it will become very expensive to do a lot of this annotation. So another alternative to this is try to do annotation as efficiently as possible. And one way you can do this is through active learning, this is a general thing. It's not only for multilingual stuff, but it's particularly useful for multilingual stuff. So I'll talk about it here. And what you do is you get some labeled data, you train a model, and then you have a whole bunch of unlabeled data. And you do data selection from that unlabeled data to try to find data that would be particularly useful for annotation. You annotate that data and you feed it back into your labeled data pool. And you get a new labeled data, and then you can do this iteration over and over and over again. So the reason why you might want to do this is if you are able to select data points well, you can get a very good result with a lot less data than if you select them poorly. And this is just an example from binary classification. So if this is the fully labeled data set, you have another data set like this. If you label 6 examples from this data set kind of at random, you might get something that's along the classification boundary here, and you have some errors. But if you select the labeled examples very well, you might get a classifier that's basically perfect and doesn't have you know, as many errors. For translation, this is particularly obvious because like in order to do translation well, you need to know how to translate words in the language, right? So if all of the words in the language are not covered in your translation data, then you're not going to do a good job. And so that's, you know, just another obvious example. There's 2 fundamental ideas in active learning. The first one is uncertainty. So we want data that are hard for our current models to handle. Because if they're easy, then we don't need to label them. The model does well on them already. And we also want representativeness. So we want data that are similar to the data that, we want data that are similar to all of the data in our unlabeled pool. And the reason why is we don't want to be getting a whole bunch of outliers, because if we get a whole bunch of outliers, those aren't going to be helpful. They're not going to generalize to new examples that we get. So these 2 things push against each other basically because models tend to be uncertain on outliers, but those are not representative, and models tend to be good at representative data because they've seen it a lot before. So you want to get something that's like a good balance of the 2, both uncertainty and representativeness. So if we look at uncertainty sampling, there's a bunch of different ways to measure uncertainty. And remember, for active learning, we don't have the labels, so we can't use the labels in calculating any of these things. So the first thing is entropy. So if we have a predictor, the predictor can calculate the probability of the labels, and we calculate the expected log likelihood of the labels and take the negative, and this is our entropy from, you know, like language modeling. And the higher the entropy, the more uncertain the model is. So we can pick higher entropy ones. Another one, which is particularly good for classification tasks, is top 1 confidence. And top 1 confidence is basically what is the confidence of the top 1 output. So we take the argmax, and then we take the log likelihood of the argmax here. And so if the model is not very confident in its top choice, then that could be a problem. Then the final one, which I think I and a lot of other people have found to be like the best choice in a lot of cases, is margin. And this is the smallest difference between the first and the second candidates, gives the most uncertainty. And this kind of makes sense, right? Because if you have a small difference between the first candidate and the second candidate, then you're more likely that, you know, a small perturbation would make you change your answer. So I tend to use the last one as my preferred method, but you can try the other ones too. Representativeness, this is a little bit tricky. So how can you classify examples as being similar to many others? The simplest way to do this is to just somehow get representations for each of the examples and try to find ones that are similar to lots of others. This paper, it was kind of a seminal paper in the field of active learning for neural models. It was done for image classification, but it's still, I think, very relevant for text if you can get good embeddings. And basically what they did is they just tried to find active learning. They tried to find examples that had good coverage of the entire feature space. And so they did kind of like k-means clustering and tried to find cluster centers and select cluster centers that weren't already, select like the centroid of clusters that weren't already well covered by the model or that had high uncertainty. So cross-lingual learning and active learning play together very well, because if you can train a cross-lingual model and then fine-tune and then use it for your initial uncertainty estimates, then you get better uncertainty estimates about what the model isn't good at. And so if you do cross-lingual learning and active learning, it works better than doing either in isolation, is what we showed in this paper. And then a recent paper that I'm actually pretty excited about is active learning for multiple languages. And the basic idea is we're moving from kind of the single language to single language transfer setting, or the multiple language to single language transfer setting that we were doing in 2019, to something where we actually want to train models that are good at like all languages, or good at like a segment of languages that your company covers, or you know, something like this. And so what you can do is you can collect data from the set of languages that you want to cover. And then you can collect data from the set of languages that you can effectively annotate. And those could be disjoint, right? You might not have any good annotators for, you know, minor languages in India or minor languages in Africa or something like that. But you can collect a lot of data, of monolingual data that you expect you would want to be able to process. And so from this, you have the target data that you want to be annotating, or sorry, that you want to be doing well at. And then you have a lot of source data that can be from any language. It doesn't even necessarily need to be the languages that you want to be good at. And then based on this, you take the target data, you take the source data, and you select a lot of data points to annotate, and you annotate it. And we demonstrate that this works well for cross-lingual learning. And we had kind of examined a whole bunch of different methods. We looked at kind of representative-based methods, uncertainty-based methods, and then representativeness plus uncertainty-based methods. And we demonstrated the kind of representativeness plus uncertainty-based methods gave the best results.